Today in this lecture we will continue waveguide theory and design. So far we have already discussed details about one dimensional optical waveguide, slab waveguide, and starting from modal analysis to dispersion curve, all those things we have discussed in the previous lecture. And today we just take from there to understand how actual practical waveguide can be implemented or designed, I would say 2D waveguide, 2D confinement. That means a mode, a guided mode will be confined in two direction and it will be allowed to propagate in the third direction. So, that is the practical waveguide we can use for photonic integrated circuits. Let us move on and let us see what all different types of waveguide is popular in photonic integrated circuit development. So, first thing is that first type of waveguide is this one. It is a cross sectional view, it is shown. So, if you consider this is x axis, this is y axis, and this is your y axis, x axis, and then z axis into the screen now. Okay. And then if you are considering it is a z propagating waveguide, then this type of cross section is continuous invariant as a function of z. And you can see that this bottom one, this is so called NS, refractive index is NS, S stands for probably substrate, and normally in our silicon dioxide, silicon on insulator, you consider that is actually buried oxide. And then actual device layer will be device or waveguide is having a little bit higher refractive index, and refractive index is ND as usual we have considered there for the device layer, and cover refractive index NC. So, this can be oxide, air, nitride, anything, okay, polymer even, all those type of things we can consider. And if you see your waveguide core, this is the waveguide core, right, this is your waveguide core. Waveguide core is buried into the substrate with a rectangular cross section. It can be any cross section, but rectangular cross section is practically easier to implement, fabricate, and that is why we consider here this rectangular or square, whatever you can design, you can do that, you are free to do so. But this type of waveguide, it is called buried channel waveguide. That means the core region is buried into the substrate, that is why buried channel waveguide, we call it buried channel waveguide. Okay. And another type of waveguide is normally popular in certain technology platform, in which you will see that the substrate it is doped with some other material, so that in a specific selected region certain atoms will be indiffused and doped, and that will enhance some refractive index. That can be graded, that means from the top to bottom, if you see that means the concentration of the doped material will be decreasing, and the refractive index change will be just proportional to the doped atoms or doped material, and that is how you get a some kind of so called graded index waveguide core, graded index waveguide core. Such a device, such a waveguide is known as diffusion doped channel waveguide. So, normally you know we have discussed about modulator, lithium niobate modulator also we discussed, and as an example I can say that if you just dope titanium, diffusion doped titanium atoms on the surface of lithium niobate substrate, suppose if it is a lithium niobate for example, okay, then titanium doping can be done you can just deposit a small layer of titanium thin film and then you put it in a furnace, then titanium will be diffused inside this lithium niobate substrate, and that concentration of the titanium actually it will be varying laterally as well as vertically, and that is how you can see the graded concentration of the titanium, and refractive index also will be proportional to the titanium atom concentration. That is how you can make a lithium niobate waveguide, and that type of waveguide is very popular for electro-optic function, electro-optic operations, particularly high speed modulator purpose. That type of waveguide it is used. So, they are called diffusion doped channel waveguide, and refractive index obviously it is some function. That function depends on what is the diffusion parameter, diffusion temperature, what is the width, etc. It can be a function of x y. We call it ND, device refractive index is a function of x y. In this case you see the core is actually step type refractive index. So, cladding to core refractive index change is abrupt, but in this case refractive index is graded. Refractive index change is graded, and ultimately towards the deep inside this refractive index will be change of the refractive index will be reducing and it will be merging to NS finally substrate refractive index. Another type of waveguide called strip waveguide, that is actually you will have substrate and then you have a device layer that is patterned like this rectangular shape, and then it will be core, and this core is now can be considered is in the top of the substrate, and it is you can have some kind of cladding material on the top. So, you can say that this core is now buried inside the upper cladding. Okay. So, this type of waveguide, since it is not buried inside the substrate, we call it strip waveguide, strip type waveguide that can be patterned. Okay. And the fourth type of waveguide, popular waveguide is this same thing, same ND material is there, core, and it is on the top of the substrate, but both side for certain application purpose you leave some here, for example, you leave some material here and you pattern like this. So, that is called rib or reed waveguide structure. Okay. These two type of waveguide structure cross section normally people use for silicon photonics application, where this photonics application, where this one will be just a box and this one will be your device layer silicon, and the top can be again SiO2, AR or silicon nitride, whatever, and you can leave some material silicon for certain kind of again electro-optic and electronic integration, electronic circuit integration, etc. You can use this device layer, and actual mode, guided mode will be confined here, surrounding region effective index will be, refractive index will be relatively lower. So, in this type of cross section, normally if you see this type of refractive index distribution, either it can be step type, it can be graded or whatever, it is only in the xy plane. What about z direction? Z direction it is invariant. So, that is why along the z direction you do not see any refractive index. You can say that if you just consider a particular coordinate, suppose you just consider this coordinate here, suppose this coordinate is x naught, y naught, and now you vary your z. Along z you will always see refractive index ND. If you consider something x1, y1 coordinate somewhere here. So, when you vary z, that means along z direction refractive index will be always NS. So, that is why it is actually called z propagating waveguide, since in the z along the z direction refractive index is not changing, only xy cross section you see refractive index change. We can say that this refractive index change that is coming out of different dielectric constant. So, dielectric constant of silicon, silicon dioxide, etc. different. Why we are writing like that? Because in the Maxwell's equation n square comes where epsilon r is there. Original Maxwell equation, it was this epsilon r is used, basically epsilon, it is epsilon equal to epsilon 0 epsilon r, as we have discussed earlier. All right. Now we say that different type of cross section, different type of platform, waveguide cross section is used for different type of technology platform, and as I mentioned that the rectangular type, this strip waveguide or this type of strip waveguide and ridge waveguide structure or rib waveguide structure is very popular for silicon photonics. So, here I try to give you a view graph, 3D view of a typical silicon photonics optical waveguides. Okay. One type of waveguide where actually you see this is the core region, it is shown here, this is your core region and this is your box layer, you can consider this is your box and this is your top cladding. Okay. Box will be NS, this will be NC and the pattern is there, rectangular pattern or square pattern, you can see that, and that is actually varied uniformly along z direction. You see it is aligned. So, that such waveguide is called actually photonic wear waveguide. Okay. And this is actually photonic wear where you are getting actually the strip, silicon strip is there, silicon strip is the core in this case. And here same thing, you have again that like a RIP type of structure, you have both sides some device layer is there, this side and this side some device layer is there, silicon is left and the height of the waveguide is same, but both side it is reduced. Okay. That is RIP type of waveguide structure, right. So, these two type of waveguide structure are popular for photonic integrated circuit. Basically, CMOS compatible silicon photonics integrated circuit, you can see this heavily used, these two types of waveguides are heavily used. Okay. Now, how this photonic wear waveguide, sometimes they are called photonic wear waveguide as I mentioned, how in this photonic wear waveguide or photonic RIP waveguide structure in silicon on insulator platform or this type of structure can be also fabricated using CMOS technology as I mentioned earlier in bulk silicon as well. In that case, the core material instead of crystalline silicon, that will be amorphous silicon and here will be this is grown oxide will be there. So, basically on the top of grown oxide polysilicon is grown deposited and polysilicon again pattern, and that polysilicon core or amorphous silicon can be patterned and that can be used as a waveguide core. Loss will be a little bit higher, but that is also used in bulk. So, what I mean to say that this type of waveguide structure you can pattern both in silicon on insulator platform as well as bulk silicon platform. So, when you can fabricate that using CMOS technology, so we need to understand that okay, we understand qualitatively that if you have a core with higher refractive index and surrounding region is lower refractive index region, that can be acted as a 2D waveguide. That means 2-dimensional confinement will be there of electromagnetic wave. So, light wave can be propagated in the jet propagating direction waveguide axis. But in such a waveguide, how to deal with that type of waveguide, how to find the solution for such waveguides. Okay. So, normally we have to develop our theory which will be compatible to a device which can be fabricated, which can be realized in practical life. Okay. So, that way we in the following today's lecture I will be discussing mostly how this mode can be calculated, how this light can be confined and how they can be useful for further applications. So, if you just take the core region only of this photonic wear waveguide structure. So, you can see that this is x axis, this is y axis. So, I just shown that x axis here and this is the z axis, this is the propagation direction. So, waveguide axis or propagation direction, waveguide axis. Okay. So, we know that any light you are launching here from this side in the xy plane from the left you are launching. So, inside in this silicon, it is a silicon core for example, it can be any other material surrounding with other lower refractive index material. Suppose this is silicon, you normally silicon ND you know that is actually 3.4778 at 1550 nanometer wavelength, 1550 nanometer wavelength. Okay. So, in that inside that material, if you just consider that wave vector any direction you consider the plane wave is entering inside, then because of the confinement total internal reflection in the xz surface. So, you have xz surface in this surface and at x equal to at y equal to 0 and y equal to say you can consider w, some w in this two interface at y equal to 0 and y equal to w. In this two interface you can see total internal reflection, and that is why you can get forward propagating and backward propagating wave vector wave in the y direction. Similarly, along x direction also you can consider the bottom is 0, x equal to 0, this thing can be considered as h, x equal to h. So, you can have x equal to 0 and x equal to h. Okay. So, you will get some kind of total internal reflection. So, that means total internal reflection also you can see in the interface in the plane in the yz plane at x equal to 0 and x equal to h. Okay. So, in that way you can get a kind of standing wave pattern, standing wave forward propagating, backward propagating, plus minus kx will be there. What we have discussed in the 1D waveguide, similar thing we can see. But along z direction you do not have any discontinuity, do not have any interface along z direction. Okay. So, it is continuous you are considering, as long as you can maintain that is continuous. That is why along z direction you have only the kz component always in the positive direction. So, if you are launching this side you can have only kz direction. If you are launching from this side, so you can have minus kz. Okay. That is the minus az you will be writing, that the unit vector will be negative, that is it. So, we know that if total internal reflection happening along x direction as well as y direction, you can have some kind of standing wave pattern along x direction as well as along y direction. So, that standing wave pattern can create some kind of field distribution inside the photonic waveguide. So, that field distribution, a particular set of kx and ky, you can have a particular solution for kz, and that particular solution of kz we can call it as a this one beta. So, that pattern will be propagating along z direction, okay, that maintaining that pattern, that is called mode, that is what we have learned so far. Okay. So, that beta we will be calling as a 2 pi by lambda n effective. N effective is known to you, effective index, right, and or that can be written as omega by c n effective. So, we will be able to get certain kind of solution omega by c n effective that will be propagating along z direction. So, again same way like whatever we have learned in 1D waveguide, here also our challenge to find out this beta value and certain pattern, whatever field distribution you will be getting in xy plane. In the xy plane you will have a certain field distribution, and corresponding that particular field distribution you will be getting a specific beta value. So, those set of field distribution, field means I mean to say electromagnetic field, electric field and magnetic field associated with a particular solution for beta, okay, that will be a mode. So, that is our challenge to find now. Okay. So, once we know that, we can use them and we can design particularly waveguide depending on the design structure, parameters, etc. we will be able to predict that what would be the mode shape, what would be the beta value, what would be the phase velocity, what would be the group velocity, what is the dispersion, etc. All sorts of things we will be able to know, and those are very, very important to design a waveguide devices using silicon photonics technology platform. Okay. Fine. So, now let us see what are the parameter, governing parameter, design parameters for silicon photonic waveguide. So, here I mentioned the design parameters of a silicon photonics optical waveguide. So, two types of waveguide I have shown, Reeve and this one. So, basically they are identical. You see, if I just try to see what are the parameters involved, first thing is that you have substrate silicon handling wafer, thickness about 500 to 750 nanometer. This is SOI substrate, right, silicon on insulator you are considering. And then you have a box layer, 2 to 3 micron typically needed. Basically more is better, but again I think 2 to 3 micron since it is sufficient. So, why to go for more, because it has to be actually grown this type of thing. So, technology for silicon on insulator platform is also very expensive. So, that wafer you need to customize, and industry has customized with 2 to 3 micron in that range somewhere. Okay. And that is basically box layer, that is silicon dioxide, and we call that as refractive index as I mentioned here, and device layer. And in the device layer if you see we can have parameters like width of the Reeve, and then device layer height h, and then another thing this small h. These 3 parameters can be considered as the waveguide parameter, geometrical parameter. In fact, you can derive this structure, photonic wave structure, once you put h, this small h equal to 0, then you get this structure. So, any way you can think of that this waveguide, this is a generic waveguide structure. So, where you can vary W value, H value, small h value, and you can design different type of waveguide cross section and different type of solutions for that also. Obviously, whenever you are buying a silicon on insulator, this part is normally constant, that is actually whatever available in the market you have to use it, or you are very much interested to do something novel, something different type of devices, you can customize that small capital H device layer thickness, or you can have your own laboratory, you can grow that way you can control that. But normally in industry today, most of the silicon photonics silicon on insulator substrate they use the device layer thickness H equal to in the order of 220 nanometer, but that is not, that also foundry to foundry, that is actually varying. Okay. Now, we have this parameter W H small h and other parameters as I mentioned, that they are refractive indices. And to solve the mode, normally ray optics picture we have already mentioned that that is not sufficient for a 1D waveguide as well. For this 2D waveguide, it is good to have directly to solve the electric field mode solution from the Maxwell's equation itself using the dielectric constant matrix like this. You can define epsilon r x y matrix in the xy plane. You can have every coordinate, you just map this one, okay, map this one, because this type of cross section you are getting from the technology point of view, right. So, you know that this is the cross section and you know this region I want to solve, what is the mode and what is the what is their propagation constant or phase velocity, etc. So, you can map this one xy coordinate wise and then you use them in Maxwell's equation to solve the rest, electric fields, propagation constant, that is it. All right. So, now if you just think about that, this epsilon r, that is actually varying in the xy plane, right. For example, you take a coordinate here, what is the refractive index Ns, you take a coordinate here, what is the refractive index, that is Nd. Okay. You take a coordinate here, refractive index Nc. You do not need to bother about what is there in the bottom, because that is just for handling purpose. So, your area where you want to solve the dielectric constant, that is this area. So, box layer, you can consider box layer, that is considered as a substrate so called for waveguide analysis, and then cladding, you can take some cladding region, and this cross section you can consider, and that cross section is invariant along z axis. So, you can imagine that this is your electric field associated with a mode. What is that? This electric field associated with a mode having a propagation constant, for example, beta of that field. You know that this field is x, y, z dependent, because all this dielectric constant is different in this cross section, and along z direction it is not changing, but z direction it is propagating, wave is propagating. We can say that this pattern x direction, y direction confinement, that will give you certain kind of pattern. That pattern function is this one. Along with that, I put a vector, because electric field will have position to position, it can have different direction, electric field direction, right. So, every point I just mentioned how electric field is there at that particular point, and that pattern will be invariant along z axis. Only difference is that it will have some kind of phase as a function of time and space as it propagates. As time passes at same coordinate, you can see how that will vary, and for same instant you will see what is the along z direction, what is their total a particular snapshot you can get. And in that particular mode, electromagnetic wave, only electric field is no meaning. You have to consider magnetic field also. For that particular mode, you will have also magnetic field, and magnetic field also will have a xy profile vector and also the same phase velocity, because they are electromagnetic wave is belong to a particular mode having a propagation constant beta. Okay. So, propagation constant will be shared by both electric field and magnetic field distribution, because that is the pattern, is called mode. Okay. So, beta will be eventually will be getting like this. It can happen that like whatever you saw in your 1D waveguide, you can have a multiple solution for n effective or beta and multiple set of this vector, and they are actually the guided mode or confined mode, you can say that. those type of solutions we have to accept. And as usual, we can say that this electric field xy dependence is there. That means this transverse electric field, transverse direction, whatever the electric field distribution, whatever xy direction your xy, but it can have Ex component, it can have Ey component, it can have a Ez component. At any point, suppose you consider this point, at this point electric field can have Y component, can have X component, and can have also Z component. Any direction it can orient. You change X different coordinate point here, there also you can consider some direction will be there, you will be getting Ex component, you will be getting certain other Ey component, and some other Ez component you will be getting. So, point to point I can have different field strength and different field strength along with the direction as well. So, I can consider that there are 3 components you can imagine in this Cartesian coordinate system for electric field. Similarly, same for magnetic field, you can have X component, Y component, Z component, that will be varying as a function of x, y, because that is a mode, and that will remain invariant along Z direction, and which will be propagating, which will be carrying energy with this phase information, okay, omega t minus beta z. So far so good. So, we have the everything is set. Now what? Now what we have to do? We have to now solve these all these 6 components. If you see all these Ex component, Ey component, Ez component, Hx component, Hy component, Hz component. So, normally all these 6 components can have in a particular mode. When we discussed about 1D waveguide, for example, in 1D waveguide, you know that 2 different types of polarization we consider, TE mode and TM mode. And in case of TE mode, we have considered only Ey component will be there for electric field. And in case of magnetic field TM polarization, TM mode, we have considered only Hy component, Y component of the magnetic field will be there, and that is how TE, TM we could decompose easily, and we analyzed them independently, individually. But when you say that is actually consistent with the Maxwell's equations for propagating energy or carrying energy in 1D waveguide, that was consistent. But when you see that light is confined in both x and y direction, and x and y direction, and you have a particular shape of the core, in that case you can imagine that in a mode all sorts of components is required for guiding purpose, for a guided mode. So, you can have all the components, and sometimes you can have a mode, maybe some of the components may be negligibly small. So, out of these 6 components, maybe 2 or 3 components you may not need to consider so small after solution, okay, you may find. But at the beginning it all depends on what is the waveguide structure, what is the refractive index distribution, what is the refractive index of the core to cladding, refractive index contrast, shape, corners, all those type of things that involve the field pattern, okay. But that field pattern actually this would be a specific type of pattern for a certain mode solutions, right. So, at the beginning we will be considering as if all the 6 components are there in the mode, and then later on we will see that for any solutions can we just can we need to consider all those modes, or some of the modes, some of all those components, or some of the components can be ignored, okay. That we will see later. For the moment, let us consider that we have to consider, we have to give equal importance to all the components, all the 6 components, Ex, Ey, Ez, and Hx, Hy, Hz. So, all these 6 components you have to consider. Good. It is not like 1D waveguide. So, now as we also mentioned that for a inhomogeneous medium, in homogeneous structure, normally we have to solve vector wave equation. Inhomogeneous in the sense that you have a pattern, you have a structure, for example, in this cross section everywhere not same refractive index, coordinate to coordinate you vary, your refractive index is different, you have this type of function. So, to deal with this type of function, we have developed from Maxwell's equation 2 vector wave equation, starting from curl equation. One, when I eliminated magnetic field, I get one vector wave equation involving electric field alone, and another equation we got that involving magnetic field alone. Here B we have placed just for used just for a very concise type of equation we get. Normally you should be finding that B equal to mu 0 mu r h. Normally mu r you are considering 1 non-magnetic material, and mu 0 is constant 4 pi into 10 to the minus 7 Henry per meter. So, basically B and H they are related with the mu naught only. So, we can just use H here, H here, H here, and mu naught can be factored out. So, instead of B I can easily write H vector here, H vector here, H vector here, that does not matter. So, it is traditionally vector wave equation is written in terms of E and B, that is why I have written here. Okay. So, we have seen how to derive this equation, these two equations earlier. I am not going into the detail again here. So, only thing is that you should keep in mind we are using this nabla square, nabla, all those type of things are there. We know what is that in Cartesian coordinate. Nabla is a vector we consider, right, a differential vector, that is actually x component will be del del x, y component will be del del y, z component del del z, and then in that case del square means del dot del, nabla dot lambda. So, that will be dot product if you take, that is actually square square square. And once you know you are getting this one, you have the mode solutions like this. So, z dependent function, the basically when something mode is propagating along z direction. So, z dependent dependency is known to you, e to the power minus j beta z, e to the power minus j beta z for a given mode. That is why del del z means if you are just making a derivative of either any magnetic field components or electric field component, if you are just making a partial derivative with respect to z, then you are going to get minus j beta. And if you do once more derivative with respect to z, then you are getting minus beta square. So, this information we know easily. So, anywhere we are facing this type of thing, suppose multiplied by, you want to operate del del square with E. So, I can write instead of that I can write minus beta square E. Okay. So, del del square you do not need to consider, because along z direction what is the variation we know, and what is their derivative, second order derivative, whatever partial second order derivative, whatever the value we know that. That is why we can just simply put to reduce the mathematical load. Fine. Now, I just again repeat it here to proceed further. Okay. So, you know that we have the epsilon r known to you. It can be matrix form or whatever it is given to you. Okay. N square x it is, you can actually extract, you can generate that matrix. If you have a cross section of the waveguide cross section, you are considering every point, you know what is the refractive index, that matrix is known to you. If it is not well defined function, right. Normally it cannot be a well defined function when you are thinking about a practical device, right. Whenever something coming practical reality, you cannot get ideal type of mathematical function type refractive index profile, right. So, you have delta epsilon r will be there, and you see in the vector wave equation for electric field, vector wave equation for magnetic field, delta epsilon r by epsilon, this term is there. We just try to see how to deal with that first, then we rest of the things we will take care. Okay. Suppose we are writing this, okay. Epsilon r can be written as n square x y, just we are writing like this, right. That is a straightforward. Now, you know this is n square numerator here. My ultimate goal is that this n square x y is in the denominator, and this is derivative. So, if you can just try to find out that here also refractive index, here also refractive index, if we can find some operator in which a single refractive index function you can operate. Okay. So, numerator let us consider, this is as if it is considered dx square type things, right. Dx square you can write, you are making derivative with respect to derivative of x with respect to x, for example. So, if you are doing derivative of x square, that you will get 2x dx, right, that type of thing you will be getting. So, you are writing this n square, this del means derivative, basically only the vector here. So, we can write n x y delta n x y. So, n square can be written as 2 times this one. So, it is something like that, x square you make a derivative, you get 2x dx. Similarly, it is a 2x, n is the x and dx is the del n x, we are writing like this, and denominator as it is we are n square x y writing. And then you see this n square, this n cancel, one n will be cancelled, then we can write 2 times delta n here and nxy. D of lnx, yeah, d of lnx, derivative of lnx is actually you can write dx by x. So, that is what we have written, 2 is there, and this is we can write like this. So, that is a one way of representation, but we will concentrate only this one. This is what we know, that what is the refractive index profile of the waveguide cross section, you know that. Okay. So, what we can write, this is actually, you see, refractive index is the xy, is a function of xy, jet invariant. So, and whenever you are taking a gradient on that, nabla operator on that, you are getting a vector, and that vector you just try to write del epsilon r, this one we can write, it will have a x component and you will have a y component. So, you get a x component with derivative this one and y component with derivative of this one refractive index. Z component also will be there, because you know this is nabla equal to ax del x plus ay, here it is written, sure, you can just follow this one. Del z, if you operate del z on nxy, because this is a function of xy only, so del z will be 0. So, we can write in that respect del z equal to 0, that is after putting that you are getting two terms, one x component term, another is y component term. So, delta epsilon r we have written this one, that will be equal to this one, this is this one, and this one we have only x component and y component will be this one. Okay. I can insert this one directly here. So, I have x component, y component, and then I have E is, for example, I have ax, ex plus ay, ey plus ez. So, if I try to get a dot product of this one, E dot delta epsilon r by epsilon r, that is what here we see. This dot product, if you see, this has only x component and y component, this has x component, y component, z component. So, ultimately you will be getting x component, that means ex, you will be getting ex times, say this component is this one, multiplication, dot product. So, accordingly you can insert there and you can find out your, try to find out your solution. Okay. So, I have repeated here, I concentrate this equation only electric field, vector equation for electric field, this one, right, del square E, this one, and this one here for magnetic field, I will consider that one later. If we consider this one and insert this one there, delta epsilon r, and what we will do, you know, this is a vector, left hand side if you consider, this will become as a vector, second term is also vector, and here E dot delta, that will be dot product of two vector, that will be a scalar, and when scalar again you are taking a gradient, that will be a vector again. So, that means this vector I can consider something like this, ax, ay, az, sorry, az, that is actually equal to 0. So, when a vector is equal to 0, what does it mean? Left hand side together it will be a vector, that vector is ultimately 0. So, you are considering this vector and adding this vector and adding this vector, you get a closed loop, for example. So, total resultant value is 0. When a vector is 0, that means individual component must be 0, x component will be 0, y component also will be 0, z component will be also 0. So, what I will be writing for a, if I just try to find out x component here, x component will be looking like this. Simply del, here del square E, this one I am writing, and del to z, del z to, you know, that is minus beta square we have written here. So, I have x 2 del x 2, second order derivative with respect to y, and with respect to z beta square is there, and in this expression one thing is missing in this, there will be epsilon r here, I will be correcting in the slide. Okay. This epsilon r will be there here, that epsilon r is written as a n square xy, okay, that is missing in this, you should keep in mind. Okay. So, nevertheless this equation is correct, omega square by c square n square xy, and then you have also other term, this term will be coming ln nxy, ln nxy, you will be getting like this, okay, that is your x component. So, that means x component I equate to 0, that is a scalar equation. You can consider only x, and uy component also of course involved. And if you are just considering y component, all the y component you add together, they must be equal to 0. Y component you take from here, y component take from here, y component take from here, they are adding together to be 0. You can write down this, you can straightforward, you just try to find out what is the x component. If you know the vector algebra, it would not be a difficult task. And similarly, you can consider z component of this thing and z component this thing, z component this thing, add them together 0. We just name equation number 1, 2 and 3. So, from here I could decompose this one into 3 scalar equation involving Ex, Ey, Ez. So, identically I can again use this equation, vector wave equation for magnetic field, and again I will be just writing, say for example, Ax Bx plus Ay By plus Az Bz equal to 0. So, that means the vector as a whole is becoming 0. All this Bx all the x component you consider from here, 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 and then add them together, Bx that must be equal to 0, By must be equal to 0, Bz must be equal to 0, right. So, that means any vector we are considering as a B, not like magnetic field here. So, all the thing again identically you try to write down for the magnetic field here. So, we can just get this thing Bx, x component, By, Bz, similar thing. It is a simple algebra, slightly different here because you have this equation and this equation, you see again missing epsilon r, you should consider that thing. Okay. So, epsilon r you considering because it is curl of curl, a vector here, that is cross, again curl of B you are considering. So, slightly different. So, if you see the 3 scalar equation coming out of electric field vector wave equation is something slightly different compared to whatever you are getting from the magnetic field vector wave equations. So, these are the things you are getting. So far so good. And then once we get these 6 components, so obviously you can say that I want to solve Ex, Ey, Ez and Hx, Hy, Hz for a given dielectric distribution across the waveguide cross section. Okay. So, that is actually possible only if you concentrate all this. You have to solve all these 6 scalar wave equation by inserting whatever nxy. If nxy known, you just insert nxy and you can solve, and normally it has to be solved numerically. And numerically whenever you are solving this, all are second order differential equation, you have to solve them simultaneously, then only these 6 components you will be getting, along with that a given beta value also as a eigen value you will be getting. These will be coming out as a eigen vector and this will be coming out as a eigen value. So, you have to solve them numerically because it is a complicated structure of the waveguide cross section, particularly this one you are getting, right, and second order derivative. So, normally Maxwell's equation if you solve, you can just solve using finite difference technique in a Fourier domain for a particular frequency of operation, then you get all these 6 equations you will be able to solve. But normally you know these you can develop your own code to solve mathematics. You can use a Python, C program, Python or C programming, etc. so that you can solve them. But I would just explain here that you do not need to solve all these 6 equations, second order differential equation. Only these 2 equations if you solve, if you get Ex and Ey from these 2 equations, equation number 1 and equation number 2 simultaneously you solve, and it is kind of whenever you are solving like you are just making some problem like Ax something a psi equal to lambda psi, something like that you will be getting equation, right. You are solving like this type of equation. You have a operator and then you are when operating and then you will be getting eigenvalue and then same if this psi is a eigenvector. So, all these components Ex and Ey components you will be getting as a eigenvector and corresponding beta value you will be getting as a eigenvalue, but you have to solve them numerically. Okay. That type of numerical program you can develop, and nowadays commercial softwares are available. You can solve directly. You just use their software and you can get to solve Ex and Ey using this 2 thing, those 2 equation if you solve. Because this 2 equation if you see, if you ignore this part, sometimes what happens if this refractive index you take ln and then again you take a derivative. Sometimes ln, if you are taking, the value will be reduced and the gradient will be reduced, and then if you take a derivative with respect to x, that is actually compared to all other terms, that can be ignored. This term can be ignored. So, in that case you have only this equation. So, only in this equation it would be easier to solve your electric field Ex component directly from equation 1. But since equation 1 and 2, it is involved, this coupled region is there, Ex Ey is coupled here, coupled term is there. So, you will not be able to use only one equation independently to solve Ex. You have to simultaneously solve equation 1 and 2 to get Ex and Ey and corresponding certain value of beta. So, using these two equations, you are set to solve Ex and Ey and beta value. These things are solved. You may get a set of solution, Ex and Ey as eigenvector, and every eigenvector you can get one solution for beta. Those are correspondingly to a particular mode for the system or structure. Okay. So, now after solving this, we are concentrating these two equations, right. Again, you just do not forget to include epsilon r here everywhere. Okay. So, both cases it is missing, and then once I know Ex, Ey, Ez, no Ez I have not solved yet, and beta I have solved. Now, we turn back to our Maxwell's equation, Gauss equation, divergence d equal to 0. What is that? If you just put divergence d, that means divergence basically epsilon r E equal to 0. Epsilon r is n square x y, epsilon r is n square x y, we write. So, divergence of this one. So, if you just expand a bit here, so you can write del del x n square E x del del y, dot product you are taking, right. So, divergence you are taking. Okay. So, you take del del x n square E x, because this is also vector E x, a x, x y, if you are just considering a y, E y, x y and a z, E z, x y, and you are taking divergence of that one, divergence of a vector. So, it is a scalar. So, you can write del del x n square time E x, del del y n square time E y, del del z n square time E z x y. Both n square is a function of x y, and we know that a solution coming out of E x and U y, they are also function of x y. Okay. So, what we know that from here, if you are taking a del del z, del del z, we know that what is the value, minus j beta. So, instead of del del z, because everywhere all the components you have this term is involved, omega t minus beta z. So, del del z means minus j beta. Okay. So, here if you are considering minus j beta times n square and E z x y, that means I can find E z x y in terms of E y and E x, n square x y known. So, every point if I have E x, this value known and of course, beta known minus j beta. So, E z x y also will be known from this expression. So, every point, every coordinate, you just insert what is the value of E x, what is the value of E y, that should be y, that should be y, E x component, E y component, right. This is x component, y component, that will be there. So, you get to know what is the E z. So, now at this point of time, you already know E x, E y, E z as well as beta known. What is left over? You need to know B x, B y and B z. So, how will you know that? You go to next thing, you turn to here also, you just consider epsilon r is there already, and you turn to another curl equation, that is curl E equal to minus j omega b. So, all the components E vector is known, I have E x, E y, E z, they are known, okay. And B means B x, B plus B y plus B z, B I can write B vector means Ax Bx plus Ay By plus Az Bz. So, I just insert E and then every component Bx I can derive Bx, By, Bz. So, Ez also known, Ey known, they are a function of xy, So, you just make a derivative and that is the rotation, Bx I can get, By I can get, Bz I can get. So, in this way I know now all Ex, Ey, Ez and Bx, By, Bz, and that is known for a given cross sectional dielectric constant distribution or refractive index distribution, and correspondingly you get a beta. A series of values you will be getting, a particular set of all the 6 components, correspondingly you will be getting 1 beta. Another set of all this you will be getting another beta. This can be considered as a eigenvector, and this can be whatever beta value you will be getting, that is as a coming as a eigenvalues. It is similar to 1D waveguide whatever we have discussed, but in this case since it is a 2-dimensional and dielectric constant is not a particular function to solve your vector wave equation. So, you have to solve it numerically. So, numerically you can solve all the things found, and these are called actually solving full vectorial wave equation. Full vectorial means all the components I am solving. Earlier in case of 1D waveguide, for TE polarization we concentrate only on Ey, and for TM polarization we concentrate on Hy, because they are the tangential component and they have been solved, and that is actually not full vectorial. You are just considering only one component and you are solving. Ultimately of course you are getting other vectors, but here directly you are using vector wave equation and you are using numerically. Of course, you may not get very accurate solutions from your numerical solutions, because your numerical solution has to be very powerful, because this is all involves differential equation. So, you have to use finite difference technique method. Sometimes some people also develop their this full vectorial equation solver using finite element method also. So, depending on the element size, depending on the element size your accuracy will depend. So, if you have a waveguide cross section, you are considering including buried oxide and then your cross section core etc. together, you are considering this area is, for example, if it is 5 micrometer by 5 micrometer area you are solving, then you can get different type of solutions. If you are going different type of solution very fast, but if you are having a very large structures and your element size is infinite is small, then you have to solve. You have to handle huge amount of data that may take longer time to solve. Nevertheless, nowadays I think plenty of companies they are offering the this type of mode solver. You can also, if you are very much passionate to develop the software, you can use your skill to develop your software to solve electric field components mode solutions as well as their propagation constant eigenvalues. So far we could actually get all these equations. 1, 2, these 2 equations gives me Ex and Ey as well as beta, and then this equation gives me Ez, and then these 3 equations gives me Bx, By, Bz. All these you will be getting, and that will be you will be getting for a particular solution beta, because Ex and Ey, Eb, beta you will be when you solve this one you will be getting a series of values. So, series of values you can index them. You can index them as a beta m, propagation constant is beta m. M can be, first one you can assign as 0 and second one it is like a 1D waveguide, you can assign as 2 etc. and for m equal to 0 you get a set of set of solutions for Ex, Ey, Ez, Bx, By, Bz, that will be corresponding to m equal to 0, 1 solution you will be getting. M equal to 1, here you will be getting 1 beta 1, here you will be getting m equal to 1, another set. So, field distribution, all the field components you will be getting as a function of x, y, and corresponding beta value you will be getting, you will be solving. Once you know that, then you can find a mode you can define like this. So, a mode, mth mode of electric field associated with the mth mode, x, y, z, you have a x dependent distribution which gives you Ex, Ey, Ez, 3 components. Each of these components it will have a different value at different point, but every point it will be oscillating with this phase part e to the power j omega t. Similarly, for magnetic field associated to the mth mode, you can have field distribution in the xy plane, x component, y component, z component. Each of them will have different value, it can be different value, but their identity is the omega t minus beta m z. So, identity of all these components carried by this one, they have a particular pattern of field distribution in the xy plane, and that pattern will be travelling with a certain phase velocity, with that phase velocity will be again Vp m, we will be writing as omega by beta m phase velocity. So now we are set, this is full vectorial method. Normally in photonic wire waveguide structure or silicon photonics waveguide, to get a solution to design a single mode guidance, or how many number of modes are there, what is the field distribution, etc. To solve, it is very difficult to solve analytically. So, you have to take help of some kind of numerical method, numerical analysis, numerical method I would say, and nowadays as I mentioned that there are plenty of softwares available, you can use them to solve field distribution. Once you know the field distribution and propagation constant, you can go for you know everything about waveguide, and now use this waveguide for developing your circuit, okay, photonic integrated circuit. So, we are very much close to develop photonic integrated circuit, and before going into that detail, we will be learning how this mode actually propagates. So, suppose you have in a waveguide, you can have a multiple modes solutions you will be getting when you solve these things. Some of them will be very confined, well defined within the waveguide, and some of them are lossy, it is just leaky modes. We will not concentrate on leaky modes, we will be exciting only the confined guided mode, and we will see that if this confined guided mode, there are 3-4 guided modes you are exciting, we would like to know how they propagate. We will show that while propagation inside the waveguide, if multiple modes are there, they do not talk each other, they do not share energy from each other, they do not interact at all, they are not coupled, they can propagate independently as an eigen mode. So, suppose you have a 5 modes, each modes carrying say for example 1 watt power, okay. Every mode is you are launching at the input side 1 watt power for mode 1, another 1 watt for mode 2, another 1 watt for mode 3. So, as long as your waveguide is maintained uniformly, that 1 watt power will be carried by mode 1, another 1 watt will be carried by another, they will not exchange their power in between, okay. That is the beauty of this eigen mode solutions you will be getting, and practically that is true. However, if your waveguide somehow it is getting disturbed, okay, then this energy exchange can take place between mode to mode, and that is very important, that is very crucial, how they are exchanging power, how you can control them, and by controlling them whether you can achieve some functionalities or not. Those things the subject of photonic integrated circuit, integrated optics. So, first in the next lecture we will be learning about this so called how these are eigen modes, and they have a specific property called orthogonality property. So, that orthogonality property first we will be discussing, and following that we will be trying to develop certain kind of coupled mode equations for understanding photonic integrated components and devices. With this I just close for this lecture, and thank you very much.